Welcome to this explainer where we're bridging the gap between basic circuits and the incredibly complex electronics powering our modern world. Today, we are demystifying a literal titan of technology, the MOSFET. If you've ever found yourself wondering exactly how your devices manage to do so much heavy lifting with such tiny, microscopic components, well, you are absolutely in the right place. Let's get into it. Here is our roadmap for today. First, we'll meet the MOSFET family. Then explore the highly versatile D-MOSFET switch, unpack its curves and bias, dive into the E-MOSFET specialist along with the math that makes it tick, and finally, we'll finish up with an ultimate transistor showdown.
Section 1, Meet the MOSFET family.
We're going to start by looking at what exactly sets this transistor family apart from older tech, like the JFET, and why it became the absolute industry standard. The acronym MOSFET stands for Metal Oxide Semiconductor Field Effect Transistor. It's a bit of a mouthful, I know, but the crucial thing to remember here is what we call the magic insulation analogy. The gate terminal is made of metal, sure, but it is physically separated from the semiconductor channel by a microscopically thin layer of silicon dioxide, which acts as an insulator. So it works exactly like a capacitor plate. It controls the current flowing through the channel using an electric field without ever actually touching it. This brilliant design gives the MOSFET an extremely high input impedance. We're talking sometimes up to 10,000 megaohms. Because of this, it draws virtually zero current from the driving circuit, making it incredibly efficient. Section 2, D-MOSFET, the versatile switch. Let's meet our first specific character in this family, the D-MOSFET. It is known for its incredible operational versatility. When you look at the physical construction of this N-channel device, alongside its schematic symbol, you'll see that yellow N region connecting the drain at the top and the source at the bottom. It literally has a built-in channel right out of the box, and you can see that reflected in the schematic symbol too. That thick, unbroken vertical line perfectly represents this continuous physical channel. It is a normally on device.
Now, because of that fully insulated gate we just talked about, we can operate the D-MOSFET in two radically different ways. First, we can apply a negative voltage to the gate. This repels electrons in the N channel, creating a depletion mode that restricts current flow. Think of it like physically squeezing a water pipe shut. Or, and this is what makes it completely unique compared to older JFETs, we can apply a positive voltage. That positive charge attracts even more free electrons into the channel, operating in enhancement mode to massively boost conductivity. It swings both ways seamlessly. Pretty cool, right?
Section 3, D-MOSFET curves and biasing. So how do we actually design circuits around this thing? Mathematically, these dual modes translate into the transconductance curve you see right here for an N-channel D-MOSFET. Notice how the curve aggressively crosses the vertical y-axis right at the IDSS point. Now, IDSS is just the baseline current when the gate voltage is exactly 0. From there, the drain current gracefully decreases to the left when the gate voltage goes negative toward the cutoff point. But if you move to the right, into positive gate voltage territory, that current sharply increases. Because the D-MOSFET so effortlessly handles both positive and negative gate voltages, engineers absolutely love to use it with this incredibly elegant and simple configuration, the zero bias circuit. Notice there is no complex voltage divider at the gate. The gate is just tied to ground through a resistor, which initially sets the gate voltage to exactly 0 volts. This sets the operating cue point right on that y-axis we just looked at. An incoming alternating current signal can then effortlessly swing the gate voltage positive and negative around that 0 point, perfectly utilizing both the depletion and enhancement modes to amplify a signal without any clipping whatsoever. Section 4, E-MOSFET, the enhancement specialist. Okay, let's shift gears to a highly specialized component that has literally revolutionized digital memory and modern computing, the E-MOSFET. Unlike the D-MOSFET we just covered, the E-MOSFET has no physical channel built in. If you look closely at the physical diagram, the P-type substrate extends all the way to that silicon dioxide insulating layer. The drain and source are completely separated. And this is perfectly reflected in the schematic symbol by that broken vertical line. The E-MOSFET is kind of what we'd call a lazy component. By default, with 0 volts on the gate,
It is completely 100% off. The current is just zero.
So, to get this transistor out of bed and actually doing some work, you absolutely must apply a very specific minimum positive voltage to the gate. This is known as the threshold voltage. It's called a threshold because it acts like a strict barrier to entry. Anything below this voltage and the transistor does absolutely nothing. But the second the gate hits this threshold, it acts like a powerful magnet, attracting electrons from the P substrate and literally inducing a temporary, thin N-channel right next to the silicon dioxide layer. Only then does the E-MOSFET wake up and allow current to flow. It operates strictly by enhancement.
Section 5. E-MOSFET biasing and math.
Since we know this device is entirely enhancement-driven and totally off at 0 volts, let's take a look at its transconductance curve to see how we calculate and bias it for real-world operation. Notice how this beautifully highlights the E-MOSFET's defining trait. Look at where the curve actually begins. The drain current remains firmly at 0 along the horizontal axis until the gate voltage hits that critical threshold voltage marker. It never intersects the vertical y-axis like the D-MOSFET did. But once you push past that threshold, the induced channel widens and the drain current just shoots upward in a steep parabolic curve. Because the curve is parabolic, calculating the exact current for any given voltage requires a little bit of math, but honestly, it's a very logical 3-step process. Step 1, you just pull a reference drain current and its corresponding gate voltage straight from the manufacturer's data sheet. Step 2, you plug those numbers into a formula to find K. Now K is a constant that is entirely specific to that individual E-MOSFET. Since no two manufacturing batches are completely identical, K helps us bridge that gap and calibrate our math to the specific physical traits of the transistor right in front of us. Finally, step 3. Once you have your K constant, you can use the transfer equation to calculate exactly what the drain current will be at any new gate voltage you choose to apply.
Furthermore, because this device is normally off, that zero bias circuit we loved so much for the D-MOSFET, completely useless here. At 0 volts, the E-MOSFET does literally nothing. So circuits have to utilize specific configurations like a voltage divider setup or the drain feedback bias shown here. By connecting the gate directly to the drain through a high-value resistor, it ensures the gate voltage is always positive enough to overcome the threshold and guarantee proper, reliable operation.
Section 6. The ultimate transistor showdown. All right, to really solidify everything we've learned in this explainer, let's put these components head-to-head. When comparing the older, traditional JFETs to our D-MOSFETs, the D-MOSFET clearly comes out on top in terms of pure capability. The JFET can only operate in depletion mode, meaning you can only squeeze the channel closed. But the D-MOSFET, it gives you dual mode flexibility. You can squeeze it closed or enhance it wide open. Plus, thanks to that silicon dioxide insulator, the D-MOSFET has an incredibly higher input impedance. The only minor drawback is that the D-MOSFET is slightly more sensitive to temperature changes than the robust old JFET.
And finally, matching the D-MOSFET against its sibling, the E-MOSFET. The stark contrast here is their default state. The D-MOSFET is an always-ready, versatile switch that loves zero-bias circuits because it can easily swing positive or negative. The E-MOSFET, on the other hand, is strictly an enhancement-only device. It requires a specific threshold voltage just to wake up, which means entirely different biasing, like drain feedback. But here's the kicker. That exact, lazy, perfectly off-default state is exactly what makes the E-MOSFET so incredibly valuable for digital logic circuits. Those circuits rely on absolutely clear, unambiguous on and off states to process binary code.
Which brings us to our conclusion. I want to leave you with this final thought to ponder. Given that E-MOSFETs draw essentially zero current at the gate and sit in a perfectly efficient default off-state saving power, they are the absolute ideal building block for digital processors. So think about this. How many billions of these microscopic E-MOSFET switches do you think are working together, flashing on and off millions of times a second inside the exact device you are using to watch this explainer right now? Well, it's likely in the tens of billions. Crazy, right? Thank you so much for joining me on this journey through the hidden architecture of our modern world. See you next time.